All right, today we are diving deep and deconstructing a classic problem. This is 1.40 from IE Irodov's legendary physics collection. Now, if you've ever tried one of these, you know they can be a real workout, so we're going to break this one down together.
For anyone who's studied physics or engineering, this book is probably familiar, i.e. Irodov's Problems in General Physics. It's kind of like a rite of passage, you know? It's famous, or maybe infamous, for problems that really push you to understand the fundamentals. Yeah, it's tough, but man, it's a legend for a reason.
And here it is. This is our puzzle for today, problem 1.40. We've got a particle moving along a circular arc, and its displacement, L, follows this specific equation, A sine omega t. Our mission? Find its acceleration at a couple of key points and figure out its absolute minimum acceleration. I know it looks a little intimidating, but trust me, we're going to take it step by step.
Okay, before we even touch the problem, we need to get our physics toolkit ready. Anytime you're dealing with motion that isn't just a straight line, you have to think about two completely different kinds of acceleration. Nailing this concept is the key to solving the whole thing. The easiest way to think about it is like you're driving a car. Tangential acceleration, that's your gas pedal. It changes how fast you're going, your speed. Normal acceleration, on the other hand, that's your steering wheel. It changes your direction, making you turn and stay on that curved road. They work together, but they do totally different jobs.
So, let's put a formal definition on it. Tangential acceleration, which we'll call Wt, is literally just the rate of change of speed. If you speak calculus, that's just the first derivative of velocity with respect to time. It always points right along the path the particle is moving. Simple as that.
And then we have its partner, normal acceleration An. You've probably also heard this called centripetal acceleration, which literally means center seeking. This is the one that's constantly pulling the particle towards the center of the circle, forcing it to turn. Its strength depends on how fast you're going, squared, and how tight the turn is.
So how do we get the total acceleration from these two pieces? Well, the great news is that the tangential and normal components are always perpendicular to each other, always at a 90-degree angle. So we can just use the good old Pythagorean theorem. The total acceleration is just the square root of yt squared plus yn squared. All right, our toolkit is officially prepped. Let's get to work and solve the first part of the problem. We need to figure out the total acceleration at two very specific spots, right at the center of the path, where displacement L is 0, and at the very ends of the swing, where L is either plus or minus a. This part is all about a little bit of calculus, but it's super logical. We start with the displacement L that they gave us. You take its derivative with respect to time, and you get velocity, v. Then you take the derivative of that to get the tangential acceleration, Wt. And finally, to get the normal acceleration, Wn, we just pop our velocity into that v squared over r formula we talked about. See? Each step just flows from the last. Now here's where the physics gets really cool. Look at what happens at these boundaries. When the particle is at the center, its speed is at its maximum. So the normal acceleration is maxed out, but the tangential acceleration is actually 0. It's not speeding up or slowing down at that instant. At the ends of the path, it's the total opposite. The particle stops for a split second, so its speed is 0, which means the normal acceleration is 0. But that's where it's changing direction the most, so its tangential acceleration is at a maximum. It's this perfect trade-off.
So, let's plug in the numbers. At those extreme points, where the particle turns around, the acceleration is purely tangential. We calculate a times omega squared, and we get our first answer, 3.2 meters per second squared.
And now for the center point, where the particle is moving fastest. Here, the acceleration is purely normal. We run the numbers through our omega n formula, and it comes out to 2.6 meters per second squared. And just like that, part A is done.
But part B? Oh, part B is where it gets really fun. We have to find the minimum possible value for the total acceleration. Now, you might think it's one of the two numbers we just found, right? But that's not always the case. The real minimum could be hiding somewhere in between those points.
So this leads to a classic calculus question. How do you find the lowest point of any function? What's the technique? Well, you take its derivative, you set that derivative to 0, and you solve. That's how you find the exact spot where the function flattens out before it starts going back up. Now, our function for total acceleration has that pesky square root in it, which can make taking a derivative a bit of a headache. So here's a little math trick. Instead of minimizing w, we can minimize w squared.
Since squaring a positive number doesn't change where its minimum is, we get the same answer, but with much, much easier algebra.
Now, we're not going to grind through every single line of the calculus. That's what scratch paper is for. But the strategy is what's brilliant. You take the equation for w squared, use a trig identity to get everything in terms of one variable, like cosine squared. Then it's just a function you can differentiate. You set that derivative to 0, solve, and that tells you the exact condition for minimum acceleration.
And after you do all that beautiful math, this is what pops out. The minimum acceleration isn't just at some random place. It happens at the very specific instant when cosine squared of omega t is equal to this value. From there, we can work backward to find the exact displacement where this magic moment occurs.
We go ahead and plug in the actual values for R and A from the problem, and we find that the minimum acceleration happens at a displacement of plus or minus 0.37 meters. And just as we suspected, look at that. It's not at the center, which was 0, and it's not at the end, which was 0.80. It's somewhere in between.
And for the final answer, we take this special displacement and plug it back into our original equation for total acceleration. And the result? 2.5 meters per second squared. And notice, that is indeed lower than the 2.6 we found at the center. So we've confirmed it really is the minimum. We found it.
So, we did it. We found all the numbers. But you know, with these Irodov problems, the final number is almost the least interesting part. The real prize, the thing you take away, is understanding the method, the strategy that got us to the answer. This problem is like a perfect blueprint for how to attack any hard physics problem. First, you identify the core physics. For us, that was the two types of acceleration. Then you grab your math tools. Calculus. You break the big problem into smaller, manageable chunks. You execute the math with care. And then at the end, you step back and make sure your answer actually makes physical sense. That's a strategy you can use anywhere.
So I want to leave you with one final thought. We've been analyzing this very abstract equation, L equals a sine of omega t. But is it just a math problem? Or does this describe something real? Well, it absolutely does. This equation is a fantastic description of how a simple pendulum swings back and forth, as long as the angle is small. The physics we just unpacked isn't trapped in a textbook, it's literally describing the world all around us. Pretty cool to think about.